Really happy to be here. And I'm going to start my talk here with a little experiment. So I went online to this website, Write with Transformer, which uses this GPT-2 model, which I'll tell you more about later. And so you go to this website and you can write something and the AI will complete for you. So I wrote, I'm going to start my talk at Data Science Portugal Day 2019 with a little help from AI. The model then prompts me to complete my sentence or continue with my talk will explore. Okay, makes sense, I accept. Explore the basics of machine learning as well as the underlying ideas about how to build models. This is a topic that I have been interested in for a while now. And this, this was not written by me, right? This was the model. So it seems like it understands where I'm coming from. And I'm going to try to explain it in a fun and interesting way. What I'm going to talk about is deep learning, blah, 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 blah. I think this is a fascinating example of the stage that we're at now with natural language models and natural language generation, and that this will be a really fun example to show here. Okay, so I'll be talking about text classification. I'm a local kid. Now I'm working in Lisbon, but I grew up here in Porto. Actually, my high school graduation ceremony was in this same room. So I'm very comfortable here. And I studied industrial engineering and management at PhilP, where I hear now they're even doing starting a master science masters, which is really cool. Didn't exist when I was studying. I worked at James, Farfetch. Now I work at Cleverly, where we mostly focus on NLP, and we develop models for our product, which is for the customer service industry. Okay. So for today, I thought this will be a good way to structure the talk would be to start with the beginning and tell you how those text models started with bag of words, naive Bayes, and so on, and then increase the complexity to these more advanced neural networks. And then at the end, a case study from my own work. So I hope there's going to be a little bit of something for everyone here, for the beginners, and then even for the more experienced people in the end. All right, so classification. It's a typical problem in machine learning. In this case, pluses and minuses. We want to find the separation or a function that allows us to classify the two. This is binary classification. What's text classification is where you have, so this is a multi-class example. For instance, you have a text snippet. I would like to order a new computer, and you want to tag it with a category, in this case, commerce. Or in the second one, we not only have one category, we have more, which can be considered a multi-label case where we predicted refund request, order issue, new order, and even we can know the probability that the model estimates for each one of those. Okay. Now, our challenge is, how do we go from having this text, right, which is represented in words, to using a machine learning model which typically deals with numbers? And we saw before, all those feature creation models and feature creation techniques and so on, which deal with numbers, right? But we have text. So first thing is we have to represent text as numbers. And a classical approach for that was the bag of words model, where you have a vector which represents your text, right? And there's each dimension in the vector could activate if a certain word is present. So in this case, we have a vector with 8 dimensions, and it's activating for the word what in the first dimension, the word is in the second dimension, and so on. So this gets very sparse, right? It's ones and zeros only. How does this look like when we have a sentence? Something like this. So the cat sat on the mat, our feature space. So if we want to transform this into a table, right? So that then we can do machine learning on it. And our table looks like what you see on the right. Those are the features. Feature number 1 activates as a 1 when the word de is present. The second feature activates when cat is present. So you see there's a 1 for the cat sat on the mat, and then also for the full stop. What's the catch here? You need as many features as words you want to represent, right? So if you have a vocabulary and you define all my texts that I want to represent have 20,000 words, your features, we're going to have 20,000 dimensions, which sometimes is not practical. But you see here the other examples and so on. Okay, also another issue is you don't know the order of the words, right? So the cat sat on the mat, if you had written the mat sat on the cat, would have the exact same representation. And then there's absolutely no machine learning model that can do anything to understand the separation between those two, because your representation doesn't differentiate that. Okay, but you can still do some interesting things. The typical model that's used as a baseline is the naive Bayes model, where you count how many times the words appear for the categories. For example, I have a category which is texts about animals. I count how many times there's the word cat in texts in observations or examples that are labeled as text about animals. I also count how many times this label text about animals appears. I do some simple math, and I get a probability for this text being something about animals versus something about drinks, which was the coffee example. All right. So now we get to the next stage. So people thought, okay, there's these problems, right? These vectors get very big, 20,000 dimensions, for example. You don't know the orders. So let's find a better representation. And that's when these dense vectors come in, the word embeddings. How do those look like? So we represent a word with a dense vector, basically. So it's not ones and zeros now, but there's a vector which tells you a little bit more about that. You can choose usually the dimensions of your embeddings. Usually it's a multiple of 2 or 16, 32, 64, which also has, we choose those numbers because of it makes it easier for the GPUs to calculate and so on. But yeah, as you can see, this is probably much more useful, right? So if you have 64 columns in your features, that's a lot simpler than dealing with 20,000 memory-wise and so on. And it's also more information there about the words. Something really cool that people found out was, so these word embeddings first started being used after this paper, Word2Vec, was published. And this was 2013, I think I had there before. And so those guys, they published this paper, Word2Vec, where they trained on a lot of data, and they had embeddings for all the words in the English language, basically. They defined, let's say, 20,000 words as well. And then they had embeddings. So basically, they had a vector representing each one of the words. So for king, they had a vector that represented that 0.1 for the first dimension, 0.5 for the second, and so on. And then they went to look for some insights into that, and they found some really cool relations. For instance, those were the vectors for king, man, woman, and queen. So you see the difference between the vector man and woman is the same for the difference between the vector king and queen, which makes sense. So they capture some semantic meaning there about the words, and it's quite amazing and interesting. While before, if you wanted to have, for example, you wanted to calculate similarity between king and man, let's say, what you will do is see how many letters are similar between king and man, and there's no letters similar. Between man and woman, there's 3 letters which are the same, so that's probably a similar word. But now, when you have those vectors, you can calculate the similarity between the dense vectors, right? And you understand that actually king and man are not that different. They're close in the space. So there's a semantic similarity. It's not a similarity in the letters that compose it, but it's a similarity in the meaning of the word. Okay. And this allows us then to build neural networks and work with neural networks much better. You could still use neural networks where you have this bag of words model as input. So imagine an input on those nodes. Instead of 3, you have 20,000 nodes. That's also possible. We also work with that sometimes, but it's not ideal, right? So you want to have an input which is limited. And that's the case when you use those dense embeddings. So now you can use, if you have, let's say, you say your maximum sentence limit is 10 words. Your input, you only need 10 nodes, and in each one of those nodes comes a vector with x dimensions, 32, 64. So here the cat sat, 3 nodes, and then the other 7 nodes would be a representation, a vector for the nothing, for nothing word. Okay, so as you can see, this is already next level, right? We went from this bag of words, naive Bayes, and now we go to neural networks. We can start using them. what happened really interesting after that was people started looking into using recurrent neural networks. Why recurrent, and what do those bring to the table? So they explore this inherent characteristic of text, which is it is sequential, right? It matters if I say the cat sat on the mat and not the mat sat on the cat or whatever. So how do those work? So for those x's there, those are inputs, input nodes. So we'll have a vector there representing the in the x1, cat on the x2, set on x3, see? But then you look at this sequentially, so that's why the network is oriented towards that direction. So what you would do is you have the input for x, you do some transformation there in the a square, and then you have this state, you also have the h0 state, which just says, okay, this sentence is beginning. And then you have the h1 state, which says, okay, I computed something around the, and this is my representation, which is a matrix, and tells you, okay, this is my state. And now you get the second input, which is cat. And you do another transformation there, but you use not only the cat vector, right? But then you get the h1 coming from the left, which tells you the previous word was the. And then you have h2 as outputs, or the next state, which already has information about the and cat. And you can do this as many times as you want, and that's why it's recurrent. And at the end, you get this state ht and the output yt, which tells you a representation of the meaning of the whole sentence. And here it matters now the order, because if you change the order, then the transformations occur differently in different places, and you have a different ht at the end. So congratulations, now we have order coming into the picture. What was the problem here? For very long sentences, the model starts to forget what happened before. So when you get to the mat at the end, the model already forgot that there was the in the beginning. And so people came up with a better solution, which are actually a solution that was already brought up before in deep learning or in neural architectures, but was not used, which was these long, short-term memory networks, which are, so those are, it's like a type of recurrent neural network. So you see, you get the input, and then the state passes on to the next, but there's more things happening in the middle. So in those, so here, inside, what happens is you have these gates that are the forget gates, input gate, and so on. And what those do is, so as the name says, forget, for example, you can trigger if there's a certain combination of parameters and inputs, then you just forget what happened there. For example, the word the, there's the cat sat on the mat. The comes up. Probably you don't want to use this because it doesn't tell you any information. Cat is much more important. So the forget gate is triggered, and it forgets that input, and you go next. So this brought another advance to the state of the art, and was really important because now you didn't have this problem of things forgetting, and you could handle longer sequences much better and focus on the right words in each sequence. Okay. I hope you're all still following. I'm going a little bit all over the history here, but let's go next then. The next step in the state of the art was the appearance of some pre-trained models and contextual words embeddings. So the first one was Elmo. So this was the name of the model, but it's also this character of Sesame Street. So here you have, it's pretty self-explanatory when you see this meme from Robin Williams asking Elmo about what's the context, the embedding for the word stick, which is a vector, remember? Now Elmo says, okay, use it in a sentence. Okay, it's in this sentence, let's stick to improvisation. Okay, in that case, this is the embedding. I think this is very clear. So the embedding is not static, it's not something that you download from the internet and exists for one word only, but it also depends on the context. It was already the case before, I forgot to mention that, with those word embeddings from Word2Vec, that you could download them from the internet. So it was a huge advancement because people at Google, Facebook, and so on trained those embeddings with a lot of text that they had, and then they just released them, and I can very easily have access to the embeddings that already have a good representation for the words in the English language, for example. Now, Elmo was the next step. Okay. At some point, there was this transformer architecture coming up, and this is really, as far as I know, more or less the state of the art. So this explored a lot this concept of attention. So in these long short-term memory networks, you still had a problem when you were, so for example, in this case, translating, if you're focusing on the word je, right, you're translating from I to je, maybe you want to not only look at the HT state, the last state in the network, but have a direct connection to the state in the beginning, and that's called attention. And this model, transformer, is very popular and is very widely used and is the base for BERT architecture, which I'm going to tell you about next. Okay, so then BERT came up. Was BERT, and yeah, this is another Sesame Street character. So you have Elmo, BERT, and you can see how interesting the lives of these people are who come up with all these names, because they're all related to Sesame Street, and our lives as well as data scientists, right? But it's funny, it's good names. So BERT was the next step. So now we have all this, it's basically a huge model. It's trained, it was released by Google, it's trained on a lot of data. They basically crunch all the data from the web, they collect it, they crunch it with lots of GPUs for lots of hours, and then they release this model with all the weights that you can download very easily and use it. It brought some new things to the table, like now you have not word embeddings, but you have sub-word embeddings. So for instance, login, login is a good example. You wouldn't have an embedding for login, but you have an embedding for log and for in. So it's tokenizing the words, it's separating them not at the word level, but at the sub-word level. This was one of the things it brought to the table in this context that people say brings it more performance and more versatility. And then it's also trained with some new tasks like predicting the next word and so on. So maybe I can tell a bit about that. So they train, for instance, BERT, they mask some words in the sentence, and then they train BERT to predict what was the word that is masked, that's hidden. And this is really a good way to train models, because you can train it unsupervised, in an unsupervised fashion, right? You just pick any random sentence, hide a word in the middle, and then train that, which was already more or less the case with word2vec. Okay, so this is the state of the art. Congrats, and now I'll tell you a bit more about this example. So BERT is, and the transformers are so there's these benchmarks where people track who's the best and who has the best models. And as you can see here, there was BERT, and then there was Facebook releasing Roberta, and now it's Albert, which is at the top. So again, very funny names, but all based on this BERT architecture. How am I using this at my work now? So I use BERT models, and I do transfer learning with them as well. So the typical case is you download this BERT model from the internet with all the weights, and then you can use it. You have your data, and you can fine-tune on your own data. You have basically a set of observations where you have labels, and you train BERT to predict those labels. But you go from the model that's already pre-trained by Google for hundreds and hundreds of hours, which has already a good understanding of the English language. There's also then BERT from different languages. And then you can train it on you can train all the layers in the model, just the last layer. There's a few different ways. So my challenge was, I have these 7,000 emails, I have categories for them, labels, and I want to train BERT on it. But then BERT sometimes has its moods, and it won't train sometimes when you have too few observations, and it's also a huge model, so with few observations, it's not working so well. So I had this challenge. But on the other hand, I had not only this data with my categories, but I had other data from the same client with 140,000 observations, and they had also a lot of categories labels, but the categories were different, okay? So I couldn't use those for my model because they were different categories. However, what we do is we trained or fine-tuned BERT with the data set too, right? So fine-tuned on that adjacent task, and the model already understands the language and the domain which we are working on. And then I fine-tune on my data set, which was the data set the smaller one, which has few observations. Because in the end, this is all the big problem is always that data is a scarce resource. Labeled data is a scarce resource and it's expensive. So if you can find these techniques, it's good. So the results are this. You see with transfer learning, we get really good results from the beginning with BERT, while BERT trained from Bayes from Google directly is the red example. And you can really see that transfer learning helped here. You also see that BERT is better than the naive Bayes models and other simple neural networks. And so you believe I didn't just do this with one data set, we also did it with other data sets. Here transferring the domain from multiple data sets in the same industry here, e-commerce, to one specific client in e-commerce space. Also, we have a lot of good results with few epochs. And the same is here. So it's an exciting time. The message I wanted to convey here is it's an exciting time to work in natural language understanding. There's a lot of exciting models that you can really easily download and use yourself. And so I encourage you to go and try it out yourself. Thank you.